So, fifth and final, you'll be pleased to hear, but something completely different. It's interesting looking at the delegate list. We've got some representatives from Cargill, very pleased to see you, who sat behind you. Representatives from universities and representatives from healthcare. Paul's trying to hide in the third row there. All in the meat industry, if you like, but they're also all in the energy industry. You're basically doing temperature control of that product that you have in your business. And this bit is about something slightly different. We've talked an awful lot about cooling down, but actually if you think, and maybe this is more obvious for something like Bacardi, bringing in raw materials at a temperature, probably ambient, and putting out finished produce at an ambient temperature, and yet such a huge energy use in between. So maybe we need to think about this slightly differently. Instead of thinking of it as consuming gas to heat things up by burning the gas, and then consuming electricity in chillers and refrigeration plants to cool them back down again, what if we could come up with a brand new idea and recover that heat and reuse it? So that's what this bit's about. I say brand new, tongue in cheek. Not too far from here in 1852, Lord Kelvin was talking about heat engines, and clearly we've got a long way to go before they're terribly commonplace. And one of the reasons for that is people think heat pumps, which is essentially just a refrigeration system, are small little devices that might sit outside your house if you've got a brand new house with underfloor heating. And we're trying to change the image of that, and this is one that we did that was displayed at the exhibition at All Energy 2 years ago. And as you can see, it's definitely not a little box that sits outside the door. The other difference is that heat pumps nowadays aren't constrained to 45 degrees. We've actually done systems much warmer than that, and the temperature keeps rising, and I think we'll be well over 100 degrees at some point fairly soon. So basically think of it as if you can cool something down, you can take the heat away from it and deliver that somewhere else. So plants are now up to 90 degrees, and this isn't just pie in the sky stuff. We've done it quite a bit. This being an obvious example that I've spoken about quite a bit over the last 7 or 8 years since this was installed in Norway. It's still the world's largest 90-degree heat pump. It's taking heat for the city out of the river, the fjord that's there. It's a fairly chilly fjord, it's only 8 degrees, and delivering that at 90 degrees for the city. So they reduced their gas consumption by 80%, they reduced their carbon footprint by 80%, and deliver much better heat going forwards. And towards the end of the presentation, I'll say why that's quite important, because we're definitely on a journey, no doubt about it. So some people say, but how does a heat pump work? Is this reverse refrigeration, or is this some sort of work of the devil or something funny like this? It's actually not. It's very simple. It's straightforward refrigeration. We've got a cold end and a warm end. The cold end on the left, where we're taking heat from somewhere, we put some work into the system through the compressor, and we make that energy move uphill by putting some work into it, and we grab it on the right hand end. Exactly the same as the fridge in your house, where the inside is cold, there's a rumbly bit at the back, the compressor that's absorbing some energy, but the heat at the back of your fridge is all the heat that went in from the supermarket shopping that you did, and the electricity all comes out as usable, discarded waste heat at the back. Air source, exactly the same. We're cooling down fresh air that's outside, and we're delivering that energy into the hot water circuit. And again, trying to get as many times the quantity of heat out as electricity in. So we pay for the electricity and we get the other stuff for free, basically. So the sciencey bit, as the shampoo commercials would say, don't be too scared of this. It's really just to demonstrate that there's basically 4 parts of the system, and these were shown in some of the other slides. We've got the compressor part at number 1, where we're putting the work or the electricity in. We've got the heat part, or the heat in, or the cooling at number 4. So in typical refrigeration, this is the bit we're interested in. And then we talked a couple of times about condensers on the roof and throwing heat away. That's this big bar along the top here. And then there's the expansion at number 3. Now we can play tunes with this, and it's been alluded to already about 1 degree or 1 Kelvin temperature drop saves energy. And that's basically because we are changing the slope of this line here. We're changing the system performance. And it basically means, much like the cars that you drive, sometimes you get better fuel economy and other times you get poorer fuel economy. You still get from A to B. It's just about doing it more effectively and more efficiently. And we can play lots of tricks in this, and the sciencey bit is adding in different components to try and play tricks on it, and really sort of, whilst as Scotty from Star Trek would say, you can't change the laws of physics. Yes, but you can make them work to your advantage. So we make the laws of physics work to our advantage, and we can do lots of different things, recovering heat from different places, Sometimes before the condenser will take some heat, sometimes after the condenser will take some heat. It's all kilowatts, and every kilowatt is a prisoner as far as we're concerned. But be careful, you can't really change the laws of physics. So there's certain rules that need to be applied. And fundamentally though, if you find heat that's warmer and you use the heat at a lower temperature, you're reducing the amount of hill climbing you have to do with the compressor. So think about the system design. So different sources, and I've spoken already about the Clyde, absolutely gigantic river, one of the largest in the UK. We're an island nation surrounded by the sea. You could not freeze the North Sea if you tried, so you could not stop taking heat out of the North Sea. It's a plentiful resource. It's effectively what was being used in Norway because it's connected to the sea. Equally though, what about waste heat? This is a picture from Grangemouth, and they're basically taking in energy, using it and then throwing it away. Now they've transformed it from a chemical base or an electricity base to waste heat, but then thrown it away. That could be collected and harvested, and we're going to have to see a lot better joined up thinking. So what did we do in Drammen? Well, it's running at 90 degrees. It's a district heating system. It's becoming a term more commonplace in the UK, but basically that means instead of having gas boilers in each of the individual houses, and in fact they don't have a gas network in Norway to speak of, they use the district heating to deliver heat to all the properties. It's a very equitable solution because the deal is that they have to sell heat for the same price as the user would have bought their other forms of energy. So it's very fair for the consumers, but equally it's very fair for the business operating it because the customers have to take a connection onto the network. Interestingly, they don't have to buy from the district heating network, so it's not completely strong-armed. They're made an offer. We'll do something that's a good deal and take it if you want it, and if you don't, that's fine, but we'll give you a good price for it. And so they're playing about with the temperatures of things. They're trying to get the temperature down all the time. We see a lot of old traditional systems in older buildings designed for 82 degrees, when actually, when you stop and think about it, we're wanting to make hot water at the taps at round about 48 degrees. If we're storing the hot water for prevention of Legionella, we're thinking round about 60 or 65 degrees. And when we're heating spaces, this room's a little bit warm for my liking, maybe it's the bright lights, but we're only heating the rooms up to 21 degrees. So do we really need to burn stuff at 1300 degrees just to get a room to 21 degrees? The answer is no. And if we think about the way the systems behave, we can get a much better outcome. So getting it down from 90 to 82 would save 8 units of saving at round about 1.5 to 3% per unit. So we can start making colossal savings just by making the systems work better. This is a couple of examples just to prove the point about the graph I was showing earlier. And at a very basic system, if we did it badly, a bit half-assed, we'd probably get an efficiency of round about 2.2. So we might get 2.2 units of heat for 1 unit of electricity by not really trying very hard. Same system, same temperatures, but we start adding in different components. We increased the efficiency to 3. We did something else, but took the first bit off in the analysis and got 2.99, and then we added them both together, and we're getting an efficiency more than 50% above where we actually were. So putting that in a graph, very basic system, not terribly well engineered, not fantastic performance, and we start playing some tunes and applying some science, we get a far better outcome. Equally though, if we've got 2 heat pumps, why put them in parallel? Why not put them in series and have one of them heating from 55 to 65 and one heating from 65 to 75? So going back to the earlier bit, one of them is now getting a 10-degree easier journey, if you like, an easier hill climb, and that's going to save at least 15% of the efficiency. It's the same kit, we've just done it in a slightly different order. So it's a bit like having your soup before your main course and your main course before your pudding. You wouldn't put them all in the one bowl and eat them all at the same time. So just applying some science. And the systems that we're now seeing are beginning to get quite large. We're way up in the tens and tens of megawatts. The quantity, and this is perhaps not evident when you read the press, about 25% of our energy consumption in this country is for electricity, and about 25% is for transport, and the other 50% is for heating. So we're beginning to see more and more people think about the way that they're heating their buildings, heating their societies by doing something better than burning gas. It's going to be a hot topic over the coming years. Going back to Drammen again, it was a very large system. We actually had 3 heat pumps and they were all working together to try and get the best possible outcome. Now, to put in context the performance at Drammen, we're getting 3 units of heat for 1 unit of electricity. That's roughly the same that you would get from a domestic heat pump, only heating to 45. So some of the points that were made about choice of working fluid, do we use an HFC or do we use ammonia? We use ammonia because it's a better working fluid with higher efficiency. We won this project in competition with an HFC by offering at least 20% better energy performance. Now that's a lot of money when you're buying electricity in the order of, I think it's about 22 gigawatt hours of electricity per year. So that's about £2.2 million if it was the UK, and we made it 20% better. So just by working a little bit harder, getting the science behind this, we did a better job for the client. We're even seeing some sites wanting to go bigger again. So I've talked about the heating bit of it, but actually the two aren't complete polar opposites. Heating and cooling are opposite sides of the same penny. If you want to do cooling, you're taking heat away from something. If you want to do heating, you're adding energy into it. And actually we can do both at the same time. So if you're running an operational site and you're doing heating and cooling, so the very first heat pump I was involved in was for a chocolate factory, and we were going to do the cooling for them, and then they said, well, we actually have to heat this stuff up before we do it. We're basically bringing in raw materials, heating them up, keeping them warm, and then cooling them down again. Could you guys deliver us heat at 60 degrees? And we said, well, we're planning to throw it away between about 30 and 40 degrees, so I don't think it'll be that much harder to get up to the higher temperature. So we basically did what's shown in the diagram here of using waste heat and the cooling effect at the same time. And that could also apply, for example, in a city. We could be, for example, doing district heating and supplying heat to the buildings, but before we throw the chilled water back into the river to cool down the fish, we could actually use that. And Drammen are beginning to put through plans. They're going to build a new hospital in the city, and it's actually going to be sited next to the district heating plant, A, because it's a short pipe to get the heat, but B, they can now take advantage of this 10 megawatts of cooling that's being thrown away. To put that in context, one of the jobs I worked on in Star many years ago was a data centre for the Royal Bank, and that was about a megawatt of cooling in a hall about the size of a football pitch. We're throwing away 10 times that quantity of cooling. And sure enough, ideas are becoming fact. Apple are building data centres in Denmark now where the waste heat is being recovered from the data centre to heat the city. So the more silly videos you look at on Facebook, the warmer your house will be. Something like that. So, a little bit of the science again. We have to be very careful when we're thinking about the energy and the terminology. We talk about COP quite a lot. It's very important not to just fall in the trap of thinking about the shaft power consumption of the compressor. You've got to think about the losses that do occur in electric motors. I didn't mention it earlier, but the motors we used in Drammen are actually water cooled, and we recover the 3% that's the waste heat. So of the electricity that goes in, 3% turns into waste heat that ordinarily would be thrown away. We're gathering that and collecting it and putting it back into the system. But nonetheless, the actual efficiency of the plant we have to think of in terms of the final COP, where we're taking inverter losses and motor losses into account. So, a couple of last slides. Well, why should we really care about these efficiencies? It's basically all about reducing our carbon footprint. You would have to be living under a rock not to have heard about the Paris Agreement and climate change. When I gave this presentation last week, I said there are only 3 countries in the world that haven't signed up to the Paris Accord. One was America, which is fairly well known. One is Syria, which has got other stuff going on. And the last is Nicaragua. Since I spoke last week, Nicaragua have signed up to the Paris Accord. So there are only 2 countries in the world that have not signed up to the Paris Accord, which is basically saying we have to have at least 80% decarbonisation of our society by 2050. To put that in context, they're actually saying, as people dig into it, and we're seeing different countries interpreting it differently, we're seeing an 80% reduction in the carbon footprint in the UK by 2040. That's 20 years from now of operation of any plants. It takes about 2 years for plants to go from idea to actual delivery. So if you started now, it'd be around about 2020, and then the plant would run for 20 years. That basically means, and just to really bring it home, that's a 5% reduction in our carbon footprint for every single one of us every year for 20 years. That is not going to be easy, especially as I just described. We're going to be 10% behind because we've been talking about it for 2 years and building stuff before we actually start. So the day you switch that plant on that you decide to do tomorrow, you've got to save 15%. So this isn't tinkering around the edges anymore. This isn't changing out a couple of light bulbs and playing around with with some controls, we have to radically reduce the carbon footprint of what we're doing. Now, the good news is the electricity grid is done very, very well. We've got a lot of renewables. We used to have what's called a grid intensity factor in the UK of 550. It's 550 grams of carbon dioxide for every 1 kilowatt hour of electricity. So a 1 bar electric fire for an hour, 550 grams. The UK has decarbonised so much. You'll have seen the news about switching off coal-fired power stations, using a bit more gas, bringing on more wind turbines. The planning consents for wind turbines compared to what we have already are very, very high. They tend to be offshore. We saw one last week was opened up, the world's first offshore floating wind farm. So there's going to be more and more low carbon sources of electricity. And that's fantastic, except if that's all we do, we'll have saved 25% of our carbon footprint. What about the other 75? The transport bit is taking a pace as well with electric cars or hydrogen cars or whatever type. But the heating bit is the major, major challenge, and we've made no progress in the last 10 years on this, save for a few biomass plants. So we've got a fundamentally different approach required to do this. So what are we seeing in terms of the actual cost? Because fundamentally, businesses run in cost. And here's 4 examples of how we could do this. We've got some very, very strong support behind this called the Renewable Heat Incentive. So basically, if you are a building, you have a choice. You can burn gas at roughly about 3 pence per unit. The boiler will be about 85% efficient, so you're making your heat for 3.5p. We can argue about the numbers later on. You've also got a carbon footprint from burning gas of around about 225 grams. If you change to electricity, then that's different. You're not burning gas anymore, but you've still got a carbon footprint, and at the moment the UK grid is 350 grams. So switching from gas to direct electricity is not going to be terribly good. It's also more expensive. It's about 10 pence for a unit of electricity, but you do get 1 unit of heat for 1 unit of electricity. If we then look at 2 different heat pumps, and one of these is playing a trick where we're recovering warm heat from the, let's say from the condenser loop, we might get an efficiency of 6 units of heat for 1 unit of electricity. Now that's great, except the way the rules were written in Brussels, and they are being changed, you don't earn the renewable heat incentive, so it's a straight play with no support, and you will take your 10p divided by 6 is 1.67 pence. Now, 1.67 pence versus 3.5 pence, that's quite good, except you've got this large asset that you have to pay for, and it doesn't tend to give you a good enough payback, but the carbon footprint is very good. It's a way less, it's a 1/7 of just, or a 1/6 of just using electricity. The last way though, the government have got carbon targets to meet. They came up with a scheme called the Renewable Heat Incentive, and that basically says we will give you a sum of money for every unit of clean heat that you do. Now, the most common one people have talked about is biomass. The fundamental challenge with that is you wouldn't be allowed to do it in a large city. It's just air pollution since we got into this game, air pollution has become an incredible problem. To put some context on that, we're seeing something like 40,000 premature deaths in the UK because of air pollution. Now, yesterday, London Mayor announced a new plan, and it's all about vehicles. Actually, in London, central London, 37% of the nitrous oxide problem is actually from burning gas. It's not from cars or taxis or buses, it's from burning gas and gas boilers and gas engines. So we're going to see pressure coming on A, the carbon footprint, and B, the air quality. But if we take this example, we will be getting 3 units of heat for 1 unit of electricity. We earn the RHI, which is an average price of about 5.5 pence. It's actually 9 pence for the first 15% of the maximum you could do in a year, and then 2.8 pence. And that would mean we're making heat at a negative price, negative 2 pence. Now that doesn't mean that you should run this thing because you'll save money. You won't. It's not quite like Northern Ireland and cash for ash as it was described, because basically after 15% of the maximum output, you will be earning 2.8 pence. It will cost you round about 3.3 pence to run the device, and then you get 2.8 pence. So it's still costing you money to make heat. So we won't see people making heat to heat open-sided chicken sheds and things like that. And we get a carbon saving. Now, what I have to point out about the grid that's gone from 550 to 350, it's still decarbonising. Right now, it's a relatively bright day, can't tell in here. It's relatively windy, so we're probably seeing a grid intensity factor right now of 250. Now, some people have apps on their phone telling you that. Nikki's going to shout out a number any moment. How much? 261 is the UK grid intensity. So if we divide 261 by 3, which is maths far too hard for me, that's about 85, we would be way below. So we'd be 0.085 grams of carbon for that 1 unit of heat. So compare that to 225. Basically doing a heat pump right now would be less than a third of, around about a third, maybe a quarter of burning gas. So this is the challenge that we're facing. So looking to the future, why that is coming to play. This is some graphs round about greenhouse gas emissions. And I've mentioned already the outcome of this, so it won't take terribly long, but basically it's an 80% reduction in our consumption of fossil fuels, unabated, and just being burned. Now, some people think, well, that means we've only got to reduce by 80%. In reality, we're going to have to keep 20% for some difficult jobs, glass making, steel making. The rest of it is going to have to be pretty much 100% reduction in our carbon footprint for heating in a very short space of time. And some scenarios have been done. For us as a business, we really like the ideas of rivers because they're out the front door, you can see them, you can get access to them relatively cheaply, and it's there. It's very predictable. You don't have to drill a hole in the ground and wonder what you might find 2 kilometres down. It's very, very straightforward and easy to do. So, is the government fully behind this? I've already mentioned the carrot, the huge amount of support that's for this. They're beginning to turn up the heat, if you pardon the pun, on the use of gas. So this is a technique which is the climate change levy. It's basically a taxation on the consumption of electricity and gas. And you'll see that it's higher for electricity than it is for gas by about 3 times. That's because electricity